Good afternoon. My name is Youngpil Jo, and I'm a PhD student undergraduate by Yunyoung Baek at Seoul National University. In this presentation, I'm going to talk about our report to improve the security level of system software on ARM-based machine. System software such as operating system and hypervisor is the most privileged software entity in the system. System software should be as secure as possible because system software is the primary measure of system resources, and trusted computing-based, less privileged software entities such as applications and guest OSs. However, many system software products adopt the monolithic design that places all subcomponents in one huge execution environment that has a same privilege level and address space. This is considered to be for performance and ease of development, but resulting in less resistance to exploit. Privilege separation, one of fundamental security principles, provides a guidance that alleviates this problem. By applying this principle to system software and separating the security critical parts of system software from the others, we can protect system software from being compromised entirely. The most intuitive and obvious approach we can use to enforce this principle to system software is to rely on more higher privileged software entity than target system software. For example, if we want to enforce this principle to operating system, then we can use hypervisor, which has a higher privilege level. But this approach has one fundamental problem, that it cannot be applied to the most privileged system software. To solve this problem, recent studies have proposed a more advanced approach we call intra-level privilege separation in this paper. This approach divides one monolithic system software into the outer domain and the inner domain. These two domains run at same processor mode and in a single address space, but they have a logically different privilege level and asymmetric memory view. The inner domain can access the outer domain's memory region without restrictions, but not vice versa. So we can securely protect the security critical parts of system software by placing them in the inner domain. At the center of intra-level privilege separation, there are two core mechanisms. First, the intra-level isolation mechanism prevents the outer domain from accessing the inner domain by forcing them asymmetric memory view. The second, the domain switching mechanism allows two domains to transfer control to each other in a secure manner. These two mechanisms determine the performance and security level of intra-level privilege separation. So hardware features, facial rating, or lightweight memory protections are essentially used for efficient and secure implementation of these mechanisms. As described in the table, various hardware features have been used in the previous works. But the fact we want to focus in this paper is the types of system software the previous work can support is determined by the used hardware feature. For example, on x86 64-bit architectures, nested kernel and hypersafe using the write protection feature can support both hypervisor and normal OS. On the other hand, on ARM's 64-bit architectures, key using the extended paging can support only the limited types of system software, namely normal OS. But in ARM's 64-bit architecture, also known as ARC64, various types of system software running at different execution level coexist to increase the functionality and security of the system. And note that any types of software may be suffer from exploits because they will most likely have vulnerabilities Therefore, we need to impose intra-level privilege separation to all types of system software to improve system security. That's why in this paper we propose a new technique called Hilps that can impose intra-level privilege separation to all types of system software running at different exception levels on ARK64. To achieve the goal of Hilps, its two core mechanisms for inter-level isolation and domain switching have to be applicable regardless of exception level. Fortunately, we found the hardware feature of ARK64 that can dynamically change the varied range of virtual address. This hardware feature, which presented all exception levels, allows Hilps to create a special memory region, temporarily accessible or inaccessible by changing the varied virtual address range. Based on such a varied virtual address range adjustment feature of ARK64, Hilps designs and implements its two core mechanisms. First, when the outer domain has control, the intra-level isolation mechanism. Intra-level isolation mechanism includes only the memory region of the outer domain into the valid virtual address range. By doing this, the outer domain is completely prevented from accessing the inner domain, where its memory region is excluded from the valid virtual address range. Now, the only way to enter the inner domain is through the domain switching mechanism. This mechanism expands the valid virtual address range to include the memory region of the inner domain and securely transfer control to the inner domain. Before looking at the implementation of these two mechanisms in detail, let me give an overview of some hardware feature of ARK64 about the address translation and virtual address range adjustment. I'll start the address translation first. ARK64 provides two main types of system registers for controlling address translation. First, TTVR0. First, the TTVR is used to point to the current page table. And TTVR is again divided into TTVR0 and TTVR1, where they are used to point to two distinct page tables, mapping the low help and the upper help virtual address spaces, respectively. Next, TCR is used to set up the details of configuration for address translation. In ARK64, these TTVR and TCR pair independently exist at all exception levels. It means that Hilps can customize the virtual address space of each system software by configuring these registers. Next, let's take a look at the virtual address range adjustment feature of ARK64. As I explained before, TCR has various configuration fields for address translation. Among them, TxSZ field relates to tuning the valid virtual address range. Recall that TCR is paired with TTVR, so TxSZ of each TCR control the valid range of the virtual address space mapped by the paired TTVR. This figure shows how a valid virtual address range varies depending on the value of TxSZ. For the low help virtual address space mapped by TTVR0, TxSZ determine the top bound, and for the upper help virtual address space mapped by TTVR1, the TxSZ determine the bottom bound. When the valid virtual address range changes, the number of valid entries of the first level page table changes proportionally. And at this point, the base entry of the first level page table entry is fixed by TTBR, so only top-bound entry changes. Based on the background information described so far, I'll explain how we first implement the intra-level isolation mechanism. First, let's assume that Hilps is applied to system software using TTBR0, such as a hypervisor. In this case, if Hilps modifies TxSZ to expand the valid virtual address range, then the valid virtual address space and the valid first level page table entries grows in the same direction. So the change of the virtual address range does not compromise the consistency of the legacy mapping between the virtual address space and the first level page table entry shown in gray in the figure. Therefore, Hilps can straightforwardly implement the intra-level isolation mechanism by doubling the valid virtual address space and placing the inner domain in the added virtual address space shown in green in the figure. Next, let's assume that Hilps is applied to system software using TTBR1, such as normal OS and secure OS. In this case, if Hilps modifies TxSZ to expand the valid virtual address range, then the valid virtual address space and the first level page table entries grows in the opposite direction. So the change of the virtual address range compromise the consistency of the legacy mapping between the virtual address space and the first level page table entry shown in gray in the figure. Therefore, even if Hilps doubles the valid virtual address space, as in the case of the TTBR0 based page table, the added virtual address space cannot be used for the inner domain. To solve this problem, Hilps expand the valid virtual address space by 4 times. By doing so, Hilps can create extra virtual address space and the first level page table shown in green in this figure that can be used for the inner domain because they don't conflict with the existing ones. In addition, Hilps copies the mapping information stored in the existing first level page table entry to the added top entries. This duplication lets Hilps be able to maintain the legacy mapping when expanding the valid virtual address range. Along with the intra-level isolation mechanism, Hilps provides the domain switching mechanism. To enter the inner domain, this mechanism first disables interrupt and changes TxSZ of TCR to reveal the inner domain by adjusting the valid virtual address range. After that, it checks whether the TCR is configured correctly and activate the inner domains stack, and finally jump to the inner domain. To return back to the outer domain, this mechanism reverses the previous procedure. It first replace the stack pointer with the outer domains and restore TCR to hide the inner domain again. And subsequently, it checks whether TCR is configured as intended and enables interrupt, and finally return to the outer domain. To evaluate the performance of Hilps, we ported Hilps to the Android Linux kernel on Juno platform. We first measure the performance of the domain switching mechanism that will have the greatest impact on system when applying Hilps on system software. As a result, the round trip between 2 domains consumes about 400 and 200 cycles in big and little cores, respectively. And we also measure the performance of it when Hilps is applied system software, particularly the Linux kernel of Android. As a result, the system core overhead. As a result, the system core overhead is about 10%, and system core overhead measured by LM bench is about 10%, and system overhead measured by several synthetic benchmarks is less than 1%. Yes, this is end of my presentation. Thank you.